that we're going to put in this column. Gravity wants to pull it down, but the air drags along that particle and pushes it up. And when those forces balance out, you basically can let it float, right? And so you have a certain minimum velocity that's associated with that point. It's the minimum fluidization velocity. And at that point, all the sand starts to kind of behave like a fluid. There's a whole bunch of benefits to that, heat transfer related, stuff like that. What we want to do is kind of look at the how the flow rate or velocity of the air kind of influences that fluidization, and seeing like how the bed height changes with respect to those increases in velocity as well. So we'll start with just a bare column with nothing in it, and we're going to be running. We have 2 vertimeters here. We plan to run, if I'm not mistaken, a number of flow rates between 5 all the way to 100 standing cubic feet per hour. So this one's basically already set for this. If we use a heavier sand, which is actually gonna bring you so we can test it, you may need more than that to get it to the fluidization point, or at least to get the full curve. If you look in the theory and you do your pre-labs, you'll see that like the delta P over L, it'll start to go up like this, and when you hit your fluidization, it'll kind of break, and then it'll basically be mostly constant after that. You should be able to see that with your data. But basically, the heavier you go with the sand, that kind of shifts that over some. So if we have to use more than that to get the full range to see the whole theoretical curve, we may need to jump higher. There's some calculations, some corrections you're going to have to make for these things, which I'll go over in a second. They're different for the different kinds, and I'll explain that too. But basically, we're trying to go in general from 5 to 100 standard cubic feet per hour and see how that influences the pressure drop, which can be the back pressure is red here, outside is atmospheric, so the delta P is just going to be what's red on your gauge. So we're measuring our velocity against that delta P. And then also the bed height. So after we start adding sand in it, so I said we're going to do just the glass column first and just see how much baseline back pressure we're going to get as we increase our flow rate. Then we're going to start adding sand to it. So we'll start with 6 inches, then 9, and I think 12. And we'll duplicate those runs, and then we'll switch to different sand. If for some reason we don't use the second sand, if we just say, well, we'll just stick to the other sand she bought, let's say it just doesn't perform super good, and we just stick to 1, we may just do 4 replicas instead of 2 of each or something like that. But plan for 2 different types of sand. So let's see what else. So these flow meters, they are calibrated for air at standard conditions. So standard conditions is going to be like STP, right? Which means it's atmospheric pressure. The thing about that is that what pressure is actually in this flow meter kind of depends on where your nozzle's at, right? Where you're controlling it, and then the back pressure ahead of it. So, for example, we have, in order to get the air supply, we have a compressor. For those of you last semester, it's going to be the same, basically the same thing. We'll plug it in. We can pressure it up. It has a safety cutoff at 120 psi. As it uses up air, it'll automatically kick back on and fill back up. It should be plenty for the low flow rates. I tested it earlier. It should be fine. You can adjust the air regular pressure with right here. Turn to the right to increase the pressure. You'll see that pressure go up here. So this is your actual tank pressure, and then you deliver pressure on this side. So this one we're going to set to about 40 psi, and then you can plug one of your quick connects into either one's fine on this side and on the back of the system over here. Once you get it pressured up, so that supply pressure coming in is going to be 40 psi. On the outside, as long as you don't have any sand or anything in it, it basically just runs through the system and comes out the top, so that's atmospheric, right? So inside of here is also essentially atmospheric, okay? So you wouldn't have to really make a correction factor for that. But when we start putting back pressure, as we increase the flow rate or start getting higher and higher with our sand, you start seeing this back pressure build up. Well, that pressure from that point, which this is underneath the system, to here, that same pressure is going to be in here too. So we're going to have to do a correction factor for whatever pressure that is. So every time the pressure goes up, you have to take that pressure, go into Excel with the correction factor. You should better look it up online. It's omegas. They're both omega. It's omega is the correction factor for variable area of the flow meters. Okay. It's pretty straightforward. It's if you see something that's like the flow rate is equal to the measured flow rate times the square root of the ratio of those pressures, the actual versus the reference pressure, which is atmosphere, something like that. That should be the right one. So for basically all pressures that we're measuring, you have to make that correction factor, but just throw it in Excel. This one's different though. So this one, you notice there's no the little valve in here. It's on the back side at the top. So because of that, your back pressure on the front end from there to here doesn't really matter at that point. The pressure inside is going to be from here back to the compressor. So whatever pressure we're setting it at, that's the one that you need to correct for, if we have to use this one. If we do, it's going to be for the heavier sand, not for the sand. Okay? So you need to correct for the and you can read that pressure back here too. If that's changing or anything, we have another pressure gauge in the back. You have to read that pressure and you have to correct it with that pressure. Okay? So two different pressures. So you just need to make sure you know which one corresponds to which flow meter. Okay? Other than that, it's pretty straightforward. You have inside the bottom that sits flat inside this silver plate. So we're measuring, when you measure the 6 inches, these should still be pretty accurate. You can double check them. But it's measured back down to sitting inside that plate. So you have basically this flow distributor. Looks like this. So it kind of makes everything evenly dispersed throughout the entire column. Column is 3-inch ID, written up here if you forget. And you can just mix the sand up and just dump it into this. I would start with nothing and start working your way up to 12. And then whenever you finish with that run, you just take the vacuum cleaner, stick it in, suck it all back out, and then just restart to get your duplicate. Same thing for the other sand. You have to be careful with the other sand though, because we don't want to mix the sands. So when you're done with one sand, we're going to make sure we clean the vacuum cleaner and dump it all back in. If you see any trash or something, I usually have like a little, see that little strainer or something like this? If you see any trash, you can kind of scoop through the sand if you want, or something like this, just to kind of keep the trash out of it and just put it back in the bucket. We'll have 2 separate buckets for the sand. Yeah. So for this one again, we're just measuring. We're setting our flow rates, and we're measuring the back pressure. This other inlet pressure, if we're using this flow meter. If not, you can just set it at 40. And then we want to measure from where the sand starts, the 6 inches or the 12 inches, whatever it is, the delta H that it rises when you increase that flow rate too. So you should have a delta P and a delta H too. Okay. We have plenty of rulers, whatever you can use. And then also while you're running it, wouldn't be a bad idea, because you have to talk about the different flow regimes it could be in, right? If it's fluidized versus like slug flow or something like that. You can take a picture or video of it as it's kind of moving around. You'll tell when it's like slug flow. You'll see like gaps between the different like chunks of sand, right? As it's kind of flopping its way through there. So it's nice to be able to have that. You might calculate it in whatever region or something like that, but then you have the picture to back that up and say, yes, this actually is what we saw with the data. That's nice to have as a comparison. So take some pictures or videos or something while you're doing it. So that's one part of this assignment. The other part is that we need to get a particle size distribution for that sand. So we have, I don't know where the SIP set is at. I don't know if we brought it back to school, but remember the SIP set? Sam might have taken it? Must have took it. Alright, we'll bring it back. Anyway. Y'all use little SIP sets before? It's basically these little brass trays that are stacked upon each other, and they have different size holes for different particles, right? They typically are bigger at the top, smaller at the bottom. And so we have this device. I'll bring it next time so y'all can see it, or you take a picture of it. But they basically just stacked up like that. You stick about 100, let's say about 100 grams or so, probably. You can weigh it out. 100 grams or so on the top, put the lid on it, and tighten it down. When you turn it on, it'll just vibrate for about 2 minutes, and it'll shake the sand all the way through. And so it'll actually split it by its particle size. So the bigger particle size is at the top, all the way to the smallest at the bottom. And then you can weigh those out and get a fractional size. You can calculate D10, D50, D90, stuff like that. And you can also get a solid mean diameter, which solid mean diameter is basically, it's a calculation with respect to the surface area to surface volume ratio, the volume to surface area ratio, and it basically gives you a reference diameter. If all the sand was the same size, which size would that be to have the similar performance to the actual mixed sand bed that you got? So that diameter is representative. If they were all the same size at that same performance, this is the size it would be, kind of. Make sense? You need to calculate one of those two. So it's two separate ports. You can do those independently. You can take half your group, start on this one, and the other group can just start taking their baseline readings and just go ahead and start with the sand. It's not a big deal. But you have to do that for both types of sand if we have both types of sand. Okay? We are planning on having two, but just in case we just use one. It'll be fine. We have everything we need, scales, we got boats. I'll bring the sieve set. I think one of our graduate students uses it for some research. I'll make sure it's all cleaned up. Again, this, you just plug it in, flip this on, it should pressure up by itself, automatic. Plug them in, show you the rotometers, you'll be good to go. Keep an eye on the pressure gauge so that you're not like exceeding the pressure. I don't think we will. Definitely not for this sand. Up to 100, it's fine. I'll test it with the heavier sand. If so, I'll just swap this out with the one that's got a bigger range. It's not a big deal. But just keep an eye on it when you're running. Make sure you don't like over flex the needle. Other than that, it's pretty straightforward. Like I said, whenever you do or start fluidizing, like the fine dust easily comes out because the air can easily take that up. It's way past its minimum fluidization point for that little bit of sand. So just if you're looking in close or whatever, just make sure you don't put your eyes too close to it or breathe in too hard. And don't put your hand too hard over the system and like put a whole bunch of back pressure on it. So just safety. Just try to think of safety things to consider. Again, this does have a safety cutoff, but if you see this going too far into the red or something like that, just turn the thing off or come get me or something. It shouldn't have to go past 120. Yeah. Any questions about the fluidization? Pretty straightforward. It's not a hard one. Okay.